Hey, this next part not so simple. Yeah, not so simple. Okay, come, let's look at it. A sample of 1 gram. Okay, let me just highlight the things. Okay, 1 gram. This 1 gram is used to calculate number of moles. Okay, we're going to divide that by the MR later on. Okay, so 1 gram of butane 2-ol is used to heat 200 cm3 of water. This is the mass that we're going to heat up. And this water, right, is at 20 degrees. The process, 75% efficient. Can be assumed that it takes 4.2 joules. Okay, guys, when they write this, right, they are trying to tell you instead of 4.18 as the heat capacity, use 4.2. Use 4.2. So please take note to use this for C. Okay, to heat up 1 cm3 of water by 1 Kelvin. This literally is the definition of heat capacity. Okay, so heat capacity, they say use 4.2. Using your answer in B part 2. So our answer in B part 2 is right here. This is for combustion of butane 2-ol. Okay, so we just put it down by the side. Combustion of butane 2-ol is equal to 2663. 2663. Okay, calculate the final temperature of water. So this question is a little bit different. Normally, we're asked to calculate the enthalpy change of combustion, right? From the MC, delta T, everything. But now, they have given to us the delta H of combustion. So we need to work from the back, right? To go back and find delta T, the change in temperature. And this change in temperature, right, will be T final minus 20 degrees. Okay, so after all our calculation with all the MC, delta T, everything, all the formula, we are going to put T final minus 20 degrees. Okay, so whatever the change is, right, you just add 20 degrees to it. That will be your final temperature. Okay, so we're going to start our journey working backwards. Number of moles, let's calculate number of moles of butane 2-ol is equals to 1/74. Okay, if you have a calculator, you can work this out. This is 0.01351. Okay, so this is the number of moles that was combusted, butane 2-ol. Okay, so we need to find Q, quantity of heat. So Q normally is equal to MC delta T, right? But in this case, we don't have delta T. So what we're going to do is we're just going to use the formula in reverse, right? Because remember, to find delta H of combustion, right, is basically Q over N. And since we have delta H combustion, we have the number of moles. We just multiply. We just multiply delta H of combustion multiplied by N. Okay, that will give us your Q. Okay, so delta H of combustion is minus 2663. Remember, you need to times 1000, yeah? Okay, because you need to convert it back. Remember, your delta H combustion is in kilojoules, right? You need to convert back to joules first. Okay, then after that, multiply by N, which is 0.01351. Okay, so as usual, if you have a calculator, do join me in calculating. Just multiply it out. Just multiply out, you should get something like 35980 joules. 35980 joules. Okay, so that is your quantity of heat that is given out by combustion. Okay, so now you have a quantity of heat given out by combustion. Now we need to find the quantity of heat that is absorbed by water. Okay, so maybe you can call that Q prime. This is the amount of heat absorbed by water. And since we know it's 75% efficient, we'll take 35980 times 0.75. Okay, so just work out the quantity of heat that's absorbed by the water. This will be 26990 joules. Okay, now we're getting very close to our answer already, right? Getting very close. We have the Q prime already. So we'll just take this Q prime, right? Divide by C times M. Okay, so we're gonna put it in an expression that you can understand. So final temperature minus 20 degrees. Remember, delta T is this expression, right? I put it down earlier. Delta T is final temperature minus 20 degrees. Okay, is equals to 26990, which is the heat that is absorbed by the water, over 4.2, the heat capacity given by the question here, heat capacity given, multiply by 200. Okay, just to jog your memory a bit, your Q is equals to MC delta T. Okay, so our delta T is this expression here. Okay, so what we did is we actually brought the MC over below the Q. Right, and just try and work out the Q, see whether you can get the final answer. What is the final temperature? This is definitely not an easy question to do, not a very easy question. But if you can do this, it will be great. Okay, guys, if you are here, can just try to work out the value for final temperature. Final temperature. Okay, so final temperature given is 52.1 degrees Celsius. Alright, so this is the final temperature after you burnt up 1 gram of butane to ore. 1 gram of butane to ore. Okay, last part of the question. The value calculated in B part 3 is not accurate. Suggest two methods that can be used to improve reliability. Oh, Sniper, you got it. Well done. Well done. Okay, two methods that can be taken to improve reliability. Okay, so basically you want to improve the reliability, right? You shouldn't say that heat loss to surrounding because definitely heat loss to surrounding is the reason. They are asking you how to improve reliability. So how do you improve, sorry, not improve, how should you prevent heat loss to surrounding? Okay, so this is a suggest question. I think every school will have slightly different answer. So the answer that I can suggest is you can use a sort of a shield when you're burning the butane to ore, or provide some leggings, means that provide some insulation. Okay, so either one of the two. In fact, they asked for two, right? Yeah, so you can give these two methods. Use a shield, all right, and to provide leggings. Okay, so that marks the end of the second structured question.